In this video, we will start to talk about a new version of linear regression that's more powerful, one that works with multiple variables or with multiple features. Here's what I mean. In the original version of linear regression that we developed, we had a single feature x, the size of the house, and we wanted to use that to predict y, the price of the house, and this was our form of our hypothesis. But now imagine what if we had not only the size of the house as a feature or as a variable with which to try to predict the price, but that we also knew the number of bedrooms, the number of houses, and the age of the home in years. It seems like this would give us a lot more information with which to predict the price. To introduce a little bit of notation, and we sort of started to talk about this earlier, I'm going to use the variables x subscript 1, x subscript 2, and so on to denote my, in this case, 4 features, and I'm going to continue to use y to denote the variable, the output variable price that we're trying to predict. Let's introduce a little bit more notation. Now that we have 4 features, I'm going to use lowercase n to denote the number of features. So in this example, we have n equals 4 because we have 1, 2, 3, 4 features, and n is different from our earlier notation where we were using m to denote the number of examples. So if you have 47 rows, m is the number of rows in this table or the number of training examples. So I'm also going to use x superscript I to denote the input features of the ith training example. As a concrete example, let's say x2 is going to be a vector of the features for my second training example, and so x2 here is going to be a vector 1, 4, 1, 6, 3, 2, 40, since those are my 4 features that I have to try to predict the price of the second house. So in this notation, the superscript, the superscript 2 here, that's an index into my training set, right? This is not x to the power of 2. Instead, this is an index that says, look at the second row of this table. This refers to my second training example. With this notation, x2 is a 4-dimensional vector. In fact, more generally, this is an n-dimensional feature vector. With this notation, x2 is now a vector, and so I'm going to use also xi subscript j to denote the value of the j of feature number j in the ith training example. So concretely, x2 subscript 3, let's say, would refer to feature number 3 in this vector, which is equal to 2. Right? And that was a 3 over there, just to fix my handwriting. So x2 subscript 3 is going to be equal to 2. Now that we have multiple features, let's talk about what the form of our hypothesis should be. Previously, this was the form of our hypothesis where x was our single feature. But now that we have multiple features, we aren't going to use this simple representation anymore. Instead, our form of the hypothesis in linear regression is going to be this. It's going to be theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x3 plus theta 4 x4. And if we have n features, then rather than summing up over our 4 features, we would have a sum over our n features. Concretely, for a particular setting of our parameters, we may have h of x equals 80 plus 0.1 x1 plus 0.01 x2 plus 3x3 minus 2 x4. This would be one example of a hypothesis. And remember, our hypothesis is trying to predict the price of the house in thousands of dollars. This is saying that the base price of a house is maybe 80,000 plus another 0.1. So that's an extra $100 per square feet. Plus the price goes up a little bit for each additional floor that the house has. So x2 was number of floors. And it goes up further for each additional bedroom the house has, because x3 was the number of bedrooms, and the price goes down a little bit with each additional age of the house, with each additional year of the age of the house. Here's the form of our hypothesis rewritten on this slide, and what I'm going to do is introduce a little bit of notation to simplify this equation. For convenience of notation, let me define x subscript 0 to be equal to 1. Concretely, this means that for every example I have a feature vector x superscript I, and x superscript I subscript 0 is going to be equal to 1. You can think of this as defining an additional 0 feature. So whereas previously I had n features x1, x2 through xn, I'm now defining an additional sort of 0 feature vector that always takes on the value of 1. So now my feature vector x becomes this n plus 1 dimensional vector that is 0 indexed. So this is now a n plus 1 dimensional feature vector, but I'm going to index it from 0. And I'm also going to think of my parameters as a vector. So my parameters here, right, that would be this theta 0, theta 1, theta 2, and so on up to theta n. I'm going to gather them up into a parameter vector written theta 0, theta 1, theta 2, and so on, down to theta n. This is another 0 index vector, so if index starting from 0, that is another n plus 1 dimensional vector. So my hypothesis can now be written theta 0 x0 plus theta 1 x1 plus dot 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 up to theta n xn. And this equation is the same as this one on top because, x0 is equal to 1. And the neat thing is I can now take this form of the hypothesis and write this as theta transpose x. Depending on how familiar you are with inner products of vectors, if you write out what theta transpose x is, what theta transpose x is this theta 0, theta 1 up to theta n. So this thing here is theta transpose, and this is actually a n plus 1 by 1 matrix. It's also called a row vector. And we take that and multiply it with the vector x, which is x0, x1, and so on down to xn. And so the inner product that is theta transpose x is just equal to this. This gives us a convenient way to write the form of the hypothesis as just the inner product between our parameter vector theta and our feature vector x, and it is this little bit of notation, this little extra bit of notational convention that let us write this in this compact form. So that's the form of our hypothesis when we have multiple features. And just to give this another name, this is also called multivariate linear regression. And the term multivariate is just maybe a fancy term for saying that we have multiple features or multiple variables with which to try to predict the value y. In the previous video, we talked about the form of the hypothesis for linear regression with multiple features, with multiple variables. In this video, let's talk about how to fit the parameters of that hypothesis. In particular, let's talk about how to use gradient descent for linear regression with multiple features. To quickly summarize our notation, this is our form of hypothesis in multivariate linear regression, where we'd adopted the convention that x0 equals 1. The parameters of this model are theta 0 through theta n. But instead of thinking of this as n separate parameters, which is valid, I'm instead going to think of the parameters as theta, where theta here is a n plus 1 dimensional vector. So I'm just going to think of the parameters of this model as itself being a vector. Our cost function is j of theta 0 through theta n, which is given by this usual sum squared error term. But again, instead of thinking of j as a function of these n plus 1 numbers, I'm going to more commonly write j as just a function of the parameter vector theta, so that theta here is a vector. Here's what gradient descent looks like. We're going to repeatedly update each parameter theta j according to theta j minus alpha times this derivative term. And once again, let me just write this as j of theta. So theta j is updated as theta j minus the learning rate alpha times the derivative or partial derivative of the cost function with respect to the parameter theta j. Let's see what this looks like when we implement gradient descent, and in particular, let's go see what that partial derivative term looks like. Here's what we have for gradient descent for the case of when we had n equals 1 feature. We had two separate update rules for the parameters theta 0 and theta 1, and hopefully these look familiar to you. And this term here was, of course, the partial derivative of the cost function with respect to the parameter theta 0. And similarly, we had a different update rule for the parameter theta 1. There's one little difference, which was that when we previously had only one feature, we would call that feature xi, but now in our new notation, we would of course call this x superscript I subscript 1 to denote our one feature. So that was for when we had only one feature. Let's look at the new algorithm for we have more than one feature, when the number of features n may be much larger than 1. We get this update rule for gradient descent, and maybe for those of you that know calculus, if you take the definition of the cost function and take the partial derivative of the cost function j with respect to the parameter theta j, you find that that partial derivative is exactly that term that I've just drawn the blue box around. And if you implement this, you will get a working implementation of gradient descent for multivariate linear regression. The last thing I want to do on this slide is give you a sense of why these new and old algorithms are, sort of the same thing, or why they're both similar algorithms, or why they're both gradient descent algorithms. Let's consider a case where we have two features, or maybe more than two features. So we have three update rules for the parameters theta 0, theta 1, theta 2, and maybe other values of theta as well. If you look at the update rule for theta 0, what you find is that this update rule here is the same as the update rule that we had previously for the case of n equals 1. And the reason that they're equivalent is, of course, because in our notational convention, we had this x0 equals 1 convention, which is why these two terms that I've drawn the magenta boxes around are equivalent. Similarly, if you look at the update rule for theta 1, you find that this term here is equivalent to the term we previously had, or the equation, the update rule we previously had for theta 1, where of course we're just using this new notation, x subscript 1, to denote our new notation for denoting the first feature. And now that we have more than one feature, we can have similar update rules for the other parameters like theta 2 and so on. There's a lot going on the slide, so so I definitely encourage you, if you need to pause the video and look at all the math on the slide slowly to make sure you understand everything that's going on here. But if you implement the algorithm written up here, then you will have a working implementation of linear regression with multiple features. In this video and in the video after this one, I want to tell you about some of the practical tricks for making gradient descent work well. In this video, I want to tell you about an idea called feature scaling. Here's the idea. If you have a problem where you have multiple features, if you make sure that the features are on a similar scale, by which I mean make sure that the different features take on similar ranges of values, then gradient descent can converge more quickly. Concretely, let's say you have a problem with two features where x1 is the size of a house and takes on values between, say, 0 to 2000, and x2 is the number of bedrooms, and maybe that takes on values between 1 and 5. If you plot the contours of the cost function j of theta, then the contours may look like this, where, let's see, j of theta is a function of parameters theta 0, theta 1, and theta 2. I'm going to ignore theta 0, so let's forget about theta 0 and pretend it's a function of only theta 1 and theta 2. But if x1 can take on a much larger range of values than x2, it turns out that the contours of the cost function j of theta can take on this sort of a very, very skewed elliptical shape. Except that with a sort of 2000 to 5 ratio, it can be even more skewed. So this very, very tall and skinny ellipses, or these very tall, skinny ovals, can form the contours of the cost function j of theta. And if you run gradient descent on this sort of cost function, your gradients may end up taking a long time and can sort of oscillate back and forth, and it can take a long time before it can finally find its way to the global minimum. In fact, you can imagine if these contours were exaggerated even more, if we were to draw incredibly skinny, tall, skinny contours, and it can be even more extreme than that, then gradient descent can just, well, it turns out gradient descent will just have a much harder time taking its way, meandering around. It can take a long time to find its way to the global minimum. In these settings, a useful thing to do is to scale the features. Concretely, if you instead define the feature x1 to be the size of the house divided by 2000, and define x2 to be maybe the number of bedrooms divided by 5, then the contours of the cost function j can become much less skewed, so the contours may look more like circles. And if you run gradient descent on a cost function like this, then gradient descent, you can show mathematically, can find a much more direct path to the global minimum rather than taking a much more convoluted path where it's sort of trying to follow a much more complicated trajectory to get to the global minimum. So by scaling the features so that they take on similar ranges of values, in this example we end up with both features x1 and x2 between 0 and 1. You can wind up with an implementation of gradient descent that can converge much faster. More generally, when we're performing feature scaling, what we often want to do is get every feature into approximately a -1 to +1 range. And concretely, your feature x0, that's always equal to 1, so that's already in that range. But you may end up dividing other features by different numbers to get them into this range. And the numbers -1 and +1 aren't too important. So if you have a feature x1 that winds up being between 0 and 3, say, that's not a problem. Or if you end up having a different feature that winds up being between -2 and positive 0.5, again, this is close enough to -1 and +1 that that's fine. I think that's fine. It's only if you have a different feature, say x3, that is between, say, that ranges from -100 to +100, then this is a very different range of values than -1 and +1. So this might be a less well-scaled feature. And similarly, if your features take on a very, very small range of values, so if x4 takes on values between -0.0001 and positive 0.0001, then again, this takes on a much smaller range of values than the -1 to +1 range. And again, I would consider this feature poorly scaled. So you want the range of values, it can be a bit bigger than +1, a bit smaller than +1, but just not much bigger like +100 here, and not too much smaller like 0.001 over there. Different people have different rules of thumb, but the one that I use is that if a feature takes on a range of values from, say, -3 to +3, I usually think that should be just fine. But maybe if it takes on much larger values than +3 or -3, I might start to worry. And if it takes on values from, say, -1/3 to 1/3, I think that's fine too. Or 0 to 1/3, or -1/3 to 0. Or just that's typical range of values I consider okay. But if it takes on a much tinier range of values like x4 here, then again I might start to worry. So the take-home message is don't worry if your features are not exactly on the same scale or exactly in the same range of values, but so long as they're all close enough to this, gradient descent should work okay. In addition to dividing by sort of the maximum value, when performing feature scaling, sometimes people will also do what's called mean normalization. And what I mean by that is that you might take a feature xi and replace it with xi minus mu I to make your features have approximately 0 mean. And obviously we won't apply this to the feature x0 because the feature x0 is always equal to 1, so it cannot have an average of value of 0. But concretely, for other features, if the range of sizes of a house takes on values between 0 to 2000, and if the average size of a house is equal to 1000, then you might use this formula, set the feature x1 to be the size minus the average value divided by 2000. And similarly, if, on average, if your houses have 1 to 5 bedrooms, and if on average a house has, say, 2 bedrooms, then you might use this formula to mean normalize your second feature x2. In both of these cases, you therefore wind up with features x1 and x2 that can take on values roughly between minus 0.5 and positive 0.5. It's actually not true. x2 can actually be slightly larger than 0.5, but close enough. And the more general rule is that you might take a feature x1 and replace it with x1 minus mu1 over s1, where to define these terms, mu1 is the average value of x1 in the training set, and S1 is the range of values of that feature. And by range, I mean, let's say, the maximum value minus the minimum value. Or for those of you that know what the standard deviation of a variable is, setting S1 to be the standard deviation of the variable would be fine too. But taking this max minus min would be fine. And similarly, for the second feature, x2, you replace x2 with this sort of subtract the mean of the feature and divide it by the range of values, meaning the max minus min. And this sort of formula will get your features, maybe not exactly, but maybe roughly into these sorts of ranges. And by the way, for those of you that are being super careful, technically, if we're taking the range as max minus min, this 5 here would actually become a 4. So if max is 5, min is 1, then the range of bedroom values is actually equal to 4. But all of these are approximate, and any value that gets the features into anything close to these sorts of ranges will do fine. And the feature scaling doesn't have to be too exact in order to get gradient descent to run quite a lot faster. So now you know about feature scaling, and if you apply this simple trick, it can make gradient descent run much faster and converge in a lot fewer iterations. That was feature scaling. In the next video, I'll tell you about another trick to make gradient descent work well in practice. In this video, I want to give you more practical tips for getting gradient descent to work. The ideas in this video will center around the learning rate alpha. Concretely, here's the gradient descent update rule. And what I want to do in this video is tell you about what I think of as debugging, and some tips for making sure that gradient descent is working correctly. And second, I want to tell you how to choose the learning rate alpha, or at least how I go about choosing it. Here's something that I often do to make sure that gradient descent is working correctly. The job of gradient descent is to find the value of theta for you that hopefully minimizes the cost function j of theta. What I often do is therefore plot the cost function j of theta as gradient descent runs. So the x-axis here is the number of iterations of gradient descent, and as gradient descent runs, you hopefully get a plot that maybe looks like this. Notice that the x-axis is number of iterations. Previously, we were looking at plots of j of theta where the x-axis, where the horizontal axis, was the parameter vector theta. But this is not what this is. Concretely, what this point is I'm going to run gradient descent for 100 iterations, and whatever value I get for theta after 100 iterations, I'm going to get some value theta after 100 iterations, and I'm going to evaluate the cost function j of theta for the value of theta I get after 100 iterations, and this vertical height is the value of j of theta for the value of theta I got after 100 iterations of gradient descent. And this point here, that corresponds to the value of j of theta for the theta that I get after I've run gradient descent for 200 iterations. So what this plot is showing the value of your cost function after each iteration of gradient descent, and if gradient descent is working properly, then j of theta should decrease after every iteration. And one useful thing that this sort of plot can tell you also is that if you look at the specific figure that I've drawn, it looks like by the time you've gotten out to maybe 300 iterations, between 300 and 400 iterations, in this segment, it looks like j of theta hasn't gone down much more. So by the time you get to 400 iterations, it looks like this curve has flattened out here. And so way out here at 400 iterations, it looks like gradient descent has more or less converged because your cost function isn't going down much more. So looking at this figure can also help you judge whether or not gradient descent has converged. By the way, the number of iterations that gradient descent takes to converge for a particular application can vary a lot. So maybe for one application, gradient descent may converge after just 30 iterations. For a different application, gradient descent may take 3,000 iterations. For another algorithm, for another learning algorithm, it may take 3 million iterations. It turns out to be very difficult to tell in advance how many iterations gradient descent needs to converge, and is usually by plotting this sort of plot. Plotting the cost function as we increase the number of iterations is usually by looking at these plots that I try to tell if gradient descent has converged. It's also possible to come up with automatic convergence tests, namely to have an algorithm try to tell you if gradient descent has converged. And here's maybe a pretty typical example of an automatic convergence test. And such a test may declare convergence if your cost function j of theta decreases by less than some small value epsilon, some small value 10 to the minus 3 in one iteration. But I find that usually choosing what this threshold is pretty difficult, and so in order to check if gradient descent is converged, I actually tend to look at plots like these, like this figure on the left, rather than rely on an automatic convergence test. Looking at this sort of figure can also tell you or give you an advance warning if maybe gradient descent is not working correctly. Concretely, if you plot j of theta as a function of the number of iterations, then, if you see a figure like this where j of theta is actually increasing, then that gives you a clear sign that gradient descent is not working. And a figure like this usually means that you should be using a learning rate alpha. If j of theta is actually increasing, the most common cause for that is if you're maybe trying to minimize a function that maybe looks like this. But if your learning rate is too big, then if you start off there, gradient descent may overshoot the minimum and send you there. And if the learning rate is too big, you may overshoot again and then send you there, and so on. So that, well, what you really wanted was for it to start here and for it to slowly go downhill, right? But if the learning rate is too big, then gradient descent can instead, keep on overshooting the minimum, so that you actually end up getting worse and worse, so sort of getting to higher values of the cost function j of theta, so that you end up with a plot like this. And if you see a plot like this, the fix usually is to just use a smaller value of alpha. Oh, and also, of course, make sure that your code does not have a bug in it, but usually too large a value of alpha is the most common, could be a common problem. Similarly, sometimes you may also see j of theta do something like this. It may go down for a while, then go up, then go down for a while, then go up, go down for a while, go up, and so on. And the fix for something like this is also to use a smaller value of alpha. I'm not going to prove it here, but under mild assumptions about the cost function j, which does hold true for linear regression, you can show, or mathematicians have shown, that if your learning rate alpha is small enough, then j of theta should decrease on every single iteration. So if this doesn't happen, probably means alpha is too big and you should set it smaller. But of course, you also don't want your learning rate to be too small, because if you were to do that, then gradient descent can be slow to converge. And if alpha were too small, you might end up starting out here, say, and end up taking just minuscule baby steps, right? And just taking a lot of iterations before you finally get to the minimum. And so if alpha is too small, gradient descent can make very slow progress and be slow to converge. To summarize, if the learning rate is too small, you can have a slow convergence problem. And if the learning rate is too large, j of theta may not decrease on every iteration, and it may not even converge. In some cases, if the learning rate is too large, slow convergence is also possible. But the more common problem you see is that j of theta may not decrease on every iteration. And in order to debug all of these things, often plotting that j of theta as a function of the number of iterations can help you figure out what's going on. Concretely, what I actually do when I run gradient descent is I would try a range of values. So just try running gradient descent with a range of values for alpha, like 0.001, 0.01. So these are a factor of 10 differences. And for these different values of alpha, just plot j of theta as a function of number of iterations. And then pick the value of alpha that seems to be causing j of theta to decrease rapidly. In fact, what I do actually isn't these steps of 10. So this is a scale factor of 10 if each step up. What I actually do is try this range of values, and so on, where this is 0.01. I'll then increase the learning rate threefold to get 0.03, and then this step up, this is another roughly threefold increase from 0.03 to 0.01, and so these are roughly trying out gradient descent with each value I try being about 3x bigger than the previous value. So what I'll do is try a range of values until I've made sure that I found one value that's too small and make sure I found one value that's too large, and then I sort of try to pick the largest possible value or just something slightly smaller than the largest reasonable value that I found. And when I do that, usually this gives me a good learning rate for my problem. And if you do this too, hopefully you'll be able to choose a good learning rate for your implementation of gradient descent. You now know about linear regression with multiple variables. In this video, I want to tell you a bit about the choice of features that you have and how you can get different learning algorithms, sometimes very powerful ones, by choosing appropriate features. And in particular, I also want to tell you about polynomial regression, which allows you to use the machinery of linear regression to fit very complicated, even very nonlinear functions. Let's take the example of predicting the price of a house. Suppose you have two features, the frontage of the house and the depth of the house. So here's a picture of the house we're trying to sell. The frontage is defined as this distance. It's basically the width or the length of how wide your lot is, of this plot of land that you own. And the depth of the house is how deep your property is. So there's a frontage, that's the depth. So you have two features called frontage and depth. You might build a linear regression model like this, where frontage is your first feature x1 and depth is your second feature x2. But when you're applying linear regression, you don't necessarily have to use just the features x1 and x2 that you're given. What you can do is actually create new features by yourself. So if I want to predict the price of a house, what I might do instead is decide that what really determines the size of a house is the area, really the land area that I own. So I might create a new feature, and just call this feature x, which is frontage times depth. This is a multiplication symbol, right? So frontage times depth, because this is the land area that I own, and I might then select my hypothesis as that, using just one feature, which is my land area, right? Because the area of a rectangle is, the product of the length of the size. So depending on what insight you might have into a particular problem, rather than just taking the features frontage and depth that we happen to have started off with, sometimes by defining new features, you might actually get a better model. Closely related to the idea of choosing your features is this idea called polynomial regression. Let's say you have a housing price data set that looks like this. Then there are a few different models you might fit to this. One thing you could do is fit a quadratic model like this. It doesn't look like a straight line fits this data very well. So maybe you want to fit a quadratic model like this, where you think the price is a quadratic function, and maybe that will give you, a fit to the data that looks like that. But then you might decide that quadratic model doesn't make sense because of a quadratic function. Eventually, this function comes back down, and well, we don't think housing prices should go down when the size goes up too high. So then maybe we might choose a different polynomial model and choose to use instead a cubic function, and where we have now a third order term, and if we fit that, maybe we would get this sort of model. And maybe the green line is a somewhat better fit to the data because it doesn't eventually come back down. So how do we actually fit a model like this to our data? using the machinery of multivariate linear regression, we can do this with a pretty simple modification to our algorithm. The form of the hypothesis we know how to fit looks like this, where we say that h of x is theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x3. And if we want to fit this cubic model that I have boxed in green, what we're saying is that the predicted price of a house is theta 0 plus theta 1 times the size of the house plus theta 2 times the square size of the house. So this term is equal to that term. And then plus theta 3 times the cube of the size of the house, right? So it's that third term. In order to map these two definitions to each other, well, the natural way to do that is to set the first feature x1 to be the size of the house, and set the second feature x2 to be the square of the size of the house, and set the third feature x3 to be the cube of the size of the house. And just by choosing my three features this way, and applying the machinery of linear regression, I can fit this model and end up with a cubic fit to my data. I just want to point out one more thing, which is that if you choose your features like this, then feature scaling becomes increasingly important. So if the size of a house ranges from 1 to 1,000, so from 1 to 1,000 square feet, say, then the size squared of the house will range from 1 to 1 million. That's the square of 1,000, and your third feature x cubed, your third feature x3, which is the size cubed of the house, will range from 1 to 10 to the 9. And so these three features take on very different ranges of values, and it's important to apply feature scaling if you're using gradient descent to get them into comparable ranges of values. Finally, here's one last example of how you really have broad choices in the features you use. Earlier we talked about how a quadratic model like this might not be ideal because maybe a quadratic model fits the data okay, but the quadratic function goes back down, and we really don't want housing prices to go down to predict that as the size of the house increases. But rather than going to a cubic model, you have maybe other choices of features, and there are many possible choices. But just to give you another example of a reasonable choice, another reasonable choice might be to say that the price of a house is theta 0 plus theta 1 times the size, and then plus theta 2 times the square root of the size, right? So the square root function is this sort of function, and maybe there will be some value of theta 1, theta 2, theta 3 that will let you take this model and fit a curve that looks like that, and goes up but doesn't, but sort of flattens out a bit and doesn't ever come back down. And so by having insight into, in this case, the shape of the square root function, and into the shape of the data by choosing different features, you can sometimes get better models. In this video, we talked about polynomial regression, that is, how to fit a polynomial like a quadratic function or a cubic function to your data. And we talked about this idea that you have a choice in what features to use, such as that instead of using the frontage and the depth of a house, maybe you can multiply them together to get a feature that captures the land area of a house. In case this seems a little bit bewildering, that, wow, we have all these different feature choices, so how do I decide what features to use? Later in this class, we'll talk about some algorithms for automatically choosing what features to use, so that you can have an algorithm look at the data and automatically choose for you whether you want to fit a quadratic function or a cubic function or something else. But until we get to those algorithms, for now, I just want you to be aware that you have a choice in what features to use, and by designing different features, you can fit more complex functions to your data than just fitting a straight line to the data. And in particular, you can fit polynomial functions as well, and sometimes by appropriate insights into the features, you can get a much better model for your data. In this video, we'll talk about the normal equation, which for some linear regression problems will give us a much better way to solve for the optimal value of the parameters theta. Concretely, so far, the algorithm that we've been using for linear regression is gradient descent, where in order to minimize the cost function j of theta, we would take this iterative algorithm that takes many steps, so multiple iterations of gradient descent, to converge to the global minimum. In contrast, the normal equation will give us a method to solve for theta analytically, so that rather than needing to run this iterative algorithm, we can instead just solve for the optimal value for theta all in one go, so that in basically one step, you get to the optimal value right there. It turns out the normal equation method has some advantages and some disadvantages, but before we get to that and talk about when you should use it, let's get some intuition about what this method does. For this explanatory example, let's take a very simplified cost function j of theta that's just a function of a real number theta. So for now, imagine that theta is just a scalar value, or that theta is just a real value. It's just a number rather than a vector. Imagine that we have a cost function j that's a quadratic function of this real valued parameter theta. So j of theta looks like that. Well, how do you minimize a quadratic function? For those of you that know a little bit of calculus, you may know that the way to minimize a function is to take derivatives and to set derivatives equal to 0. So if you take the derivative of j with respect to the parameter theta, you get some formula, which I'm not going to derive, and then you set that derivative equal to 0, and this allows you to solve for the value of theta that minimizes j of theta. That was the simpler case of when theta is just a real number. In the problem that we're interested in, theta is no longer just a real number, but instead is this n+1 dimensional parameter vector. And our cost function j is a function of this vector value of theta 0 through theta m, and the cost function looks like this sum squared cost function on the right. How do we minimize this cost function j? Calculus actually tells us that one way to do so is to take the partial derivative of j with respect to every parameter theta j in turn, and then to set all of these to 0. If you do that and you solve for the values of theta 0, theta 1 up to theta n, then this will give you the values of theta that minimize the cost function j. Well, if you actually work through the calculus and work through the solution to the parameters theta 0 through theta n, the derivation ends up being somewhat involved. And what I'm going to do in this video is actually to not go through the derivation, which is kind of long and kind of involved. But what I want to do is just tell you what you need to know in order to implement this process so that you can solve for the values of the thetas that corresponds to where the partial derivative is equal to 0, or alternatively, or equivalently, the values of thetas that minimize the cost function j of theta. And I realize some of the comments I may have made more sense only to those of you that are a little more familiar with calculus. So, but if you don't know, if you're less familiar with calculus, don't worry about it. I'm just going to tell you what you need to know in order to implement this algorithm and get it to work. For the example that I want to use as a running example, let's say that I have m equals 4 training examples. In order to implement this normal equation method, what I'm going to do is the following. I'm going to take my data set. So here are my 4 training examples. In this case, let's assume that these 4 examples is all the data I have. Okay. What I'm going to do is take my data set and add an extra column that corresponds to my extra feature x0 that's always takes on this value of 1. What I'm going to do is I'm then going to construct a matrix called capital X. That's a matrix that basically contains all of the features for my training data. So concretely, here are all my features. I'm going to take all those numbers and put them into this matrix X. Okay, so just copy the data over one column at a time. And then I'm going to do something similar for y. So I'm going to take the values I'm trying to predict and construct now a vector like so, and call that a vector y. So x is going to be a m by n+1 dimensional matrix, and y is going to be a m dimensional vector, where m is the number of training examples and n is the number of features. And I have n+1 because of this extra feature x0 that I added. Finally, if you take your matrix X and you take your vector Y, and if you just compute this and set theta to be equal to x transpose x inverse times x transpose Y, this will give you the value of theta that minimizes your cost function. There was a lot that happened on this slide, and I worked through it using one specific example of one data set. Let me just write this out in a slightly more general form, and then later on in this video, let me explain this equation a little bit more in case it's not yet entirely clear how to do this. In the general case, let's say we have m training examples, so x1, y1 up to xm, ym, and n features. So each of our training examples, xi, may look like a vector like this. There's an n+1 dimensional feature vector. The way I'm going to construct the matrix X, this is also called the design matrix, is as follows. Each training example gives me a feature vector like this. That's this sort of n+1 dimensional vector. The way I'm going to construct my design matrix X is I'm going to construct a matrix like this. And what I'm going to do is take the first training example, so that's a vector, take its transpose, so it ends up being this long flat thing, and make x1 transpose the first row of my design matrix X. Then I'm going to take my second training example, x2, take the transpose of that, and put that as the second row of X, and so on, down until my last training example, take the transpose of that, and that's my last row of my matrix X. And so this makes my matrix X an m by n+1 dimensional matrix. As a concrete example, let's say I have only one feature, only one feature other than x0, which is always equal to 1. So if my feature vectors xi are equal to this 1, which is x0, and then some row feature like maybe the size of the house, then my design matrix X would be equal to this. For the first row, I'm going to basically take this and take its transpose. So I'm going to end up with 1, and then x1, 1. For the second row, I'm going to end up with 1, and then x1, 2, and so on down to 1, and then x1, m. And thus this will be a m by 2-dimensional matrix. So that's how I construct the matrix X. And the vector Y, sometimes I might write an arrow on top to denote that it's a vector, but very often I'll just write this as Y either way. The vector Y is obtained by taking all the labels, all the correct prices of houses in my training set, and just stacking them up into an m-dimensional vector, and that's Y. Finally, having constructed the matrix X and the vector Y, we then just compute theta as X transpose X inverse times X transpose Y. I just want to make sure that this equation makes sense to you and that you know how to implement it. So, concretely, what is this X transpose X inverse? Well, X transpose X inverse is the inverse of the matrix X transpose X. Concretely, if you were to say set A to be equal to X transpose times X, so X transpose is a matrix, X transpose times X gives you another matrix, and we'll call that matrix A, then, X transpose X inverse is just, you take this matrix A and you invert it, right? It's equal to, let's say, A inverse, and so that's how you compute this thing. You compute X transpose X, and then you compute its inverse. We haven't yet talked about octave. We'll do so in a later set of videos, but in the octave programming language, or similarly in also the MATLAB programming language is very similar. The command to compute this quantity, I guess really this quantity, X transpose X inverse times X transpose Y, is as follows. In octave, X prime is the notation that you use to denote X transpose, and so this expression that's boxing in red, that's computing X transpose times X. P_inv is a function for computing the inverse of a matrix, so this computes X transpose X inverse, and then you multiply that by X transpose, and you multiply that by Y, so you end up computing that formula, which I didn't prove, but it is possible to show mathematically, even though I'm not going to do so here, that this formula gives you the optimal value of theta, in the sense that this, if you set theta equal to this, that's the value of theta that minimizes the cost function j of theta for linear regression. One last detail. In an earlier video, I talked about feature scaling and the idea of getting features to be on similar ranges of scales or similar ranges of values of each other. If you're using this normal equation method, then feature scaling isn't actually necessary and is actually okay if, say, some feature x1 is between 0 and 1, and some feature x2 is between, ranges from 0 to 1000, and some feature x3 ranges from 0 to 10 to the minus 5. And if you're using the normal equation method, this is okay, and there's no need to do feature scaling. Although, of course, if you were using gradient descent, then feature scaling is still important. Finally, when should you use gradient descent and when should you use the normal equation method? Here are some of their advantages and disadvantages. Let's say you have m training examples and n features. One disadvantage of gradient descent is that you need to choose the learning rate alpha, and often this means running it a few times with different learning rate alphas and then seeing what works best. And so that's a lot of extra work and extra hassle. Another disadvantage of gradient descent is that it needs many iterations, and so depending on the details, that could make it slower, although there's more to the story, as we'll see in a second. As for the normal equation, you don't need to choose any learning rate alpha, so that makes it really convenient, makes it simpler to implement. You just run it, and it usually just works. And you don't need to iterate, so you don't need to plot j of theta, check for convergence, and take all those extra steps. So far, the balance seems to favor the normal equation. Here are some disadvantages of the normal equation and some advantages of gradient descent. Gradient descent works pretty well even when you have a very large number of features. So even if you have millions of features, you can run gradient descent and it'll be reasonably efficient and it'll do something reasonable. In contrast, the normal equation, in order to solve for the parameters theta, we need to solve for this term. We need to compute this term x transpose x inverse. This matrix x transpose x, that's an n by n matrix if you have n features, because if you look at the dimensions of x transpose dimensions of x, you figure out what the dimension of the product is. The matrix x transpose x is an n by n matrix, where n is the number of features. And on most computer implementations, the cost of inverting a matrix grows roughly as the cube of the dimension of the matrix. So computing this inverse costs roughly order n cubed time. Sometimes it's slightly faster than n cubed, but it's close enough for our purposes. So if n is the number of features is very large, then computing this quantity can be slow, and the normal equation method can actually be much slower. So if n is large, then I might usually use gradient descent because we don't want to pay this order n cubed time. But as n is relatively small, then the normal equation might give you a better way to solve the parameters. What does small and large mean? Well, if n is on the order of 100, then inverting a 100 by 100 matrix is no problem by modern computing standards. If n is 1000, I would still use the normal equation method. Inverting a 1000 by 1000 matrix is actually really fast in a modern computer. If n is 10,000, then I might start to wonder. Inverting a 10,000 by 10,000 matrix starts to get kind of slow, and I might then start to maybe lean in the direction of gradient descent, but maybe not quite. N equals 10,000, you can sort of invert a 10,000 by 10,000 matrix. But if it gets much bigger than that, then I would probably use gradient descent. So if n equals 10 to the 6, if you have a million features, then inverting a million by million matrix, it's going to be very expensive, and I would definitely favor gradient descent if you have that many features. So exactly how large your set of features has to be before you convert to gradient descent, I don't know. It's hard to give a strict number, but for me, it's usually around 10,000. But I might start to consider switching over to gradient descent, or maybe to some other algorithms that we'll talk about later in this class. To summarize, so long as the number of features is not too large, the normal equation gives us a great alternative method to solve for the parameters theta. Concretely, so long as the number of features is less than 1,000, I would usually just use the normal equation method rather than gradient descent. To preview some ideas that we'll talk about later in this course, as we get to the more complex learning algorithm, for example, when we talk about classification algorithms like a logistic regression algorithm, we'll see that those algorithms actually, the normal equation method actually do not work for those more sophisticated learning algorithms, and we will have to resort to gradient descent for those algorithms. So gradient descent is a very useful algorithm to know, both for linear regression when we have a large number of features, and for some of the other algorithms that we'll see in this course, because for them the normal equation method just doesn't apply, it doesn't work. But for the specific model of linear regression, the normal equation can give you a alternative that can be much faster than gradient descent. And so depending on the details of your algorithm, depending on the details of your problem and how many features you have, both of these algorithms are well worth knowing about. In this video, I want to talk about the normal equation and non-invertibility. This is a somewhat more advanced concept, but it's something that I've often been asked about, and so I want to talk about here and address it here. But this is a somewhat more advanced concept, so feel free to consider this optional material. And it's a phenomenon that you may run into that's maybe somewhat useful to understand, but even if you don't understand the normal equation and linear regression, you should really get that to work okay. Here's the issue. For those of you that are maybe somewhat more familiar with linear algebra, what some students have asked me is, when computing this theta equals x transpose x inverse x transpose y, what if the matrix x transpose x is non-invertible? So for those of you that know a bit more linear algebra, you may know that only some matrices are invertible and some matrices do not have an inverse. We call those non-invertible matrices singular or degenerate matrices. The issue or the problem of x transpose x being non-invertible should happen pretty rarely. And in Octave, if you implement this to compute theta, it turns out that this will actually do the right thing. I'm getting a little technical now, and I don't want to go into the details, but Octave has two functions for inverting matrices. One is called pinv, and the other is called inv. And the differences between these two are somewhat technical. One's called the pseudo-inverse, one's called the inverse. But you can show mathematically that so long as you use the pinv function, then this will actually compute the value of theta that you want, even if x transpose x is non-invertible. The specific details between what is the difference between pinv and what is inv, that's somewhat advanced numerical computing concepts that I don't really want to get into. But I thought in this optional video, I'll try to give you a little bit of intuition about what it means for x transpose x to be non-invertible, for those of you that know a bit more linear algebra and might be interested. I'm not going to prove this mathematically, but if x transpose x is non-invertible, there are usually two most common causes for this. The first cause is if somehow in your learning problem you have redundant features. Concretely, if you're trying to predict housing prices, and if x1 is the size of the house in feet, in square feet, and x2 is the size of the house in square meters, then 1 meter is equal to 3.28 feet, rounded to 2 decimals. And so your two features will always satisfy the constraint that x1 equals 3.28 squared times x2. And you can show, for those of you that are, this is somewhat advanced linear algebra now, but if you're an expert in linear algebra, you can actually show that if your two features are related via a linear equation like this, then the matrix x transpose x will be non-invertible. The second thing that can cause x transpose x to be non-invertible is if you're trying to run a learning algorithm with a lot of features. Concretely, if m is less than or equal to n. For example, if you imagine that you have m equals 10 training examples, but you have n equals 100 features, then you're trying to fit a parameter vector theta, which is n plus 1 dimensional, so it's 101 dimensional. You're trying to fit 101 parameters from just 10 training examples. And this turns out to sometimes work, but to not always be a good idea, because as we'll see later, you might not have enough data if you have only 10 examples to fit 100 or 101 parameters. We'll see later in this course why this might be too little data to fit this many parameters. But commonly what we do then, if m is less than n, is to see if we can either delete some features or to use a technique called regularization, which is something that we'll talk about later in this course as well, that will kind of let you fit a lot of parameters, use a lot of features, even if you have a relatively small training set. But this regularization will be a later topic in this course. But to summarize, if ever you find that x transpose x is singular, or alternatively you find it is non-invertible, what I would recommend you do is first look at your features and see if you have redundant features like this x1, x2, being linearly dependent or being a linear function of each other like so. And if you do have redundant features, and if you just delete one of these features, you really don't need both of these features. If you just delete one of these features, that would solve your non-invertibility problem. And so I would first think through my features and check if any are redundant, and if so, then keep deleting redundant features until they're no longer redundant. And if your features are not redundant, I would check if I might have too many features, and if that's the case, I would either delete some features if I can bear to use fewer features, or else I would consider using regularization, which is this topic that we'll talk about later. So that's it for the normal equation and what it means for if the matrix x transpose x is non-invertible. But this is a problem that you should run, that hopefully you run into pretty rarely. And if you just implement it in Octave using the pin function, which is called the pseudo-inverse function. So if you use a different linear algebra library, it's called a pseudo-inverse. But that implementation should just do the right thing, even if x transpose x is non-invertible, which should happen pretty rarely anyway, so this should not be a problem for most implementations of linear regression.